Hello everyone! My name is Julia and I'm here to talk about the ecology of the deep sea. It can be argued that the final frontier is not outer space, but the depths of our own planet Earth. Apart from the fact that humans can't breathe underwater, it's both expensive and difficult to build submersibles that will not collapse under the immense hydrostatic pressure that builds up the deeper one goes. Considering that the ocean covers approximately 71% of the planet, scientists estimate that only 1% of the seafloor has been explored. Today we will be taking a dive down to explore the parts of the ocean already known. But keep in mind that this is only a small percent of what is down there. There is so much more to discover. Okay, here we go! To make studying the ocean easier, scientists have divided it into several oceanic zones. There are two main horizontal zones. The coastal zone reaches from the shore to the low tide mark. Then the pelagic zone comes next and is divided into two subcategories. The neritic zone consists of water overlying the continental shelf, usually about 600 feet out from the low tide mark. The oceanic zone is water past the continental shelf, over the continental slope, in the ocean floor. It is characterized by darkness and high pressure. There are also two main vertical zones, the euphotic and aphotic zones. The euphotic zone is defined as deep as an organism can live and still have enough light to support photosynthesis. It usually ends at about 500 feet deep. A subcategory within the euphotic zone is the neustic zone, which is the surface of the water. Today, when I mention the deep sea, I'm referring to anything in the aphotic zone. The second zone, or the aphotic zone, is aptly named because there is not enough light for photosynthesis. Ecosystems in the aphotic zone often utilize chemosynthesis and detritus as bases for their food chains. The aphotic zone is divided further into four subcategories. The mesopelagic zone extends from about 500 to 3,280 feet deep. Then the bathopelagic zone continues from 3,280 to 13,000 feet deep. Next, the abyssopelagic zone consists of water from 13,000 to 20,000 feet deep. And finally, the hadal zone extends from 20,000 to 35,000 feet. The name for the hadal zone is derived from Hades, which is the Greek word for hell. Yikes! So next time someone tells you to go to hell, just let them know that scientists are trying, but the technology simply isn't there yet. Additionally, the benthic zone is defined as the bottom of the water column you are studying, regardless of depth. It can be found at 15 feet deep or 15,000 feet deep. As I said before, the reason why these extreme depths are so hard to explore is because as depth increases, so does pressure. That is why scuba divers have to pay close attention and ensure that their lungs do not expand or collapse too rapidly. The equation for the hydrostatic pressure of seawater at any given depth is the depth that one is at times the density of seawater times the gravitational constant of the Earth. For example, to find the hydrostatic pressure at the bottom of Marianas Trench, one of the deepest oceanic trenches in the world, you would take the depth of the bottom, which is about 10,990 meters, times the density of seawater, and the average density of seawater is 1,027 kilograms per meters cubed, times the gravitational constant of the Earth, which is 9.81 meters per second squared. The pressure at the bottom of Marianas Trench can be estimated to be about 110,722,821 newtons per meter squared. That is why deep sea exploration can be so dangerous. To study the ecology of the deep sea, one must be familiar with the different geological formations found on the sea floor. Because all organisms adapt to live most efficiently in their environments, to be knowledgeable of these habitats makes studying the different ecosystems found there easier. The first type of formation with an ecosystem that we are going to study is called an abyssal plain. Abyssal plains are muddy, underwater plains between 3,000 and 6,000 meters deep. They are estimated to cover about 60% of the Earth's surface. Another formation that we will be covering is called a seamount. Seamounts form from volcanic activity and the buildup of hardened lava. Because of this, seamounts can be found at a variety of depths and even form islands. The third type of formation we'll be covering is called a hydrothermal vent. These are often called black smokers because they look like chimneys. Like seamounts, they are the result of volcanic activity. They churn out water 300 to 400 degrees Celsius. Minerals in the water precipitate when they come in contact with the cold seawater. Columns and spires are formed that give them the chimney look. The final formation we are covering is called a cold seep. Cold seeps are natural deposits of oil and gas, particularly hydrogen sulfide, methane, and hydrocarbon fluids that seep out of the earth. The seepage is called a brine pool. At a first glance, abyssal plains look, well, abysmal. Ha 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 ha. They appear to be barren, muddy expanses, but they're actually lively ecosystems. Echinoderms, for example starfish and sea urchins, are common down here. Other creatures seen here include sea slugs, crabs, shrimp, worms, other bottom-feeding fish, and bacteria. They rely on the organic molecules from falling detritus, for example, dead organisms or feces that fall from shallow waters for energy. Creatures will sometimes hold onto rocks and filter food sources from the water. Because seamounts are at various depths, ecosystems on them can vary. One common factor to all seamounts is that they are home to many endemic species. Seamounts are often isolated from each other, like underwater islands. The creatures that live on them can only live at a certain depth because of the amount of light that their food chain requires. We see the process of natural selection coming into play as organisms adapt to their specific seamounts. In 1977, hydrothermal vents were discovered in an aphotic zone. They had long red tube worms growing off them. These worms puzzled scientists because they had no digestive tracts to metabolize detritus. Turns out, bacteria living in the tube worms use oxygen and hydrogen sulfide from the vents to turn detritus into usable energy. Looking closer, the bacteria oxidizes the sulfide to make sugars. Carbon dioxide, hydrogen sulfide, and oxygen form sulfur, sugar, and water. This process is called chemosynthesis because bacteria in the tube worms are using chemical energy to create food. This is special because now scientists know that food chains exist that are entirely independent of the sun. Biologists also found archaea, crabs, slugs, fish, and shrimp living with the tube worms. Ecosystems living on top of cold seeps also utilize chemosynthesis. For example, tube worms are found in the Gulf of Mexico that use bacteria to digest brine pools. The bacteria burn hydrocarbons, oxidizing oil and gas, and releasing hydrogen sulfide. A bicarbonate shell is left behind. Ancient reefs form on the shell. For example, sea whips and sea corals form. They rely on carbon from falling detritus to live. These in turn provide a home for crabs, fish, anemones, and even sharks to live. In total, these reefs can take over 100,000 years to develop. Unfortunately, the biodiversity of the deep sea faces many threats. Cold seep ecosystems are damaged by the drilling of deep-sea oil rigs, especially in the Gulf of Mexico, where oil rigs are quite common. When a deep-sea rig explodes, ancient habitats are destroyed. In addition, new technologies have been created to strip mine hydrothermal vents. Mining companies want the valuable precipitates released from the vents. Sadly, the new technologies invented will destroy the organisms that live on them in the process. Climate change is also very dangerous to the deep sea. The excess of man-made carbon dioxide in the atmosphere is turning the oceans extra acidic, hurting corals and other calcifying organisms when they try to create their bicarbonate skeletons. As corals are an important part of food chains in reef ecosystems, many creatures are put in jeopardy as a result. Just because we can't see the deep sea or have as much information about it does not mean that there is nothing in the depths to protect. There is not as much media and appreciation of the biodiversity in the deep sea as there should be. This makes it easier for commercial ventures to exploit it. The deep sea is one of the last places on Earth not touched by humans. How terrible would it be if humans destroy everything in the deep before we can even explore it? The mysteries of the deep sea could hold incredible resources and knowledge, but we might destroy it first.